Hello friends, now we will see one university solved example on matrix displacement method. This is the university question. It is a two-span continuous beam. One span is loaded with 200 kilonewton at the mid-span. The other span is loaded with uniformly distributed load of intensity 60 kilonewton meter. Here the support, middle support is a sinking support. There is a settlement in the order of 1000 by EI. This is the value of the settlement. At A, the vertical displacement is 0. Rotation is also 0. These are all prescribed displacements. Similarly, at B, the prescribed displacement is 1000 by EI in the vertical direction due to settlement. But there is a displacement in the form of rotation. There is a rotation at support B. Similarly, at support C, also there is a displacement in the form of rotation. It is theta C. These are the two displacements. So the degree of freedom is 2. That is theta B and theta C. This is displacement number 1, theta B. Displacement number 2 is theta C. I will briefly explain the various steps involved in solving this problem. All the associated explanations can be referred in this website shown here, rgnsite.wordpress.com. rgnsite.wordpress.com will give you all the associated explanations, not only in this subject, but also on RCC design, steel design, strength of materials, structural analysis 1 and 2. Further, the very same page also can be picked up from this website. The download is free. The first step is calculation of fixed end moment, MFAB. It is the load, point load at midspan, WL by 8. MFAB is anti-clockwise moment, so negative sign. Then B is settled. So MF, the moment at A due to settlement is also anti-clockwise. That is given as 6E8 delta by L square. Here L is 8. Delta is 1000 by EI, the settlement value. 6EI is the formula. EI gets cancelled. So this is the total fixed end moment at EA, MFAB. Then MFBA. We are calculating these moments as if all the ends are fixed and the fixed end moments are calculated. MFBA is WL by 8. This is clockwise moment, so it is positive. As I told, when the support B settles with respect to A, the moment is anti-clockwise at both A and B. That is 6E8 delta by L square. So the net moment is 106.25. It is positive value. The settlement moment are explained in the website. I have already explained. You can see this settlement value here. B is settled by an amount of delta with respect to A. B is settled by an amount of delta with respect to C also. So the deflected shape will be something like this. As a result of which, here also the moment is anti-clockwise. At A also the moment is anti-clockwise. Similarly, on BC, the right hand side of support B, the deflected shape is somewhat like this. So the moment is clockwise both at B and C. And the moment value is minus 6E8 delta by L square for anti-clockwise moments and 6E8 delta by L square for clockwise moments, which is applicable for M of BC and M of CB. For further explanations, you can refer the website I have told, rgnsite.wordpress.com. This is the website. So I will proceed briefly explaining the various steps involved. Having calculated the fixed end moments, we have to calculate the unbalanced moments at 2 points, B and C. These are the points where displacements are present, theta B and theta C. This is delta 1 and this is delta 2, and F1 is the unbalanced moment. That is the sum of the two moments, M of BA and M of BC. M of BA is 106.25, M of BC is minus 440. So this is the unbalanced moment. Similarly, F2 is this refers to the point number 2, displacement 2, that is theta C, this point. Here the unbalanced moment is only one moment is there, that is 560 kilonewton meter. These are the unbalanced moments which have been introduced because of the fixity assumptions we have made. We have to deduce the actual beam from the assumed fixed beam. In the assumed fixed beam, these unbalanced moments are there. These moments should go. In the assumed beams, theta B, theta C, the rotations have been restrained because we have assumed as if they are fixed. Now we have to introduce the rotations theta B and theta C. That is one condition, and the unbalanced moments also should go off. So because of the rotations theta B and theta C induced, moments are caused, and these moments will be equal and opposite to this unbalanced moment, and that is the basic equation. K times delta is equal to the force, unbalanced force. Now this K is the movement introduced due to unit rotation, but we have to introduce the rotation theta B. Theta B is nothing but the delta 1, that is theta B into the movement due to unit rotation. The movement due to unit rotation is K11. So that multiplied by theta 1 will give you the movement caused by theta B. Similarly, we have to find out the movement due to theta C. We have got the stiffness coefficients, which are nothing but the movements caused by unit movement. So for getting the total movement, we have to multiply by the rotation theta C. This should be equal to the unbalanced movement. This is the basic equation. Now I will explain the stiffness coefficients. K11. What does it mean? K11 means the movement caused at point 1 due to rotation applied at 1. The second subscript refers to the point where the rotation is applied. The first subscript refers to the point where the moment is induced. K11 means moment induced at 1 due to rotation applied at 1. Now that is equal to 4EI by L on one side and 4EI by L on the other side. The rotation is applied at B and the moment is measured at the near end. Therefore, it is the formula is 4EI by L. 4EI by L. L is this on left hand side. Similarly, 4EI by L. This is 10 meter on the right hand side. Rotation is applied here. Unit rotation is applied at B, and we are calculating the moment induced at B. This is the near side. So the formula is 4EI by L on this side and 4EI by L on this side. That is what has been written here. 4EI by 8 plus 4EI by 10, it adds to 0.9 EI. The second stiffness coefficient K12 refers to the rotation induced, unit rotation induced at 2 and the moment induced at 1. 2 is the point where the rotation is induced. Sorry, this that is 1. K12. We are first calculating K12. K1 is the point where the rotation is applied. 2 is the point where the moment is induced. K21 is equal to 2EI by 10. That is we are applying the rotation at B, and we are calculating the movement at 2. This is point number 1 and this is point number 2. So here you are applying the unit rotation. That is, 1 is the point where the rotation is applied. 2 is the displacement number, that is theta c. You are calculating the moment induced at 2. That is this point. So that is equal to 2EI by L. This is farther side. This is 1, displacement number 1. This is displacement number 2. You are applying unit rotation at B and calculating the moment induced at 2. It is far side moment. So the formula is 2EI by L. K21 we are calculating. That is equal to 2EI by 10. And K12, as per Maxwell's law, K12 is equal to K21. Now we will come to the other stiffness, K22. K22 is the second substitute 2. This refers to the point where unit rotation is applied, and first substitute denotes the point where the moment is induced. K22 means the unit rotation is applied at 2 and moment is measured at 2. That is, this is the near side. So it is 4EI by L. 4EI by 10. It comes to 0.418. Now what about the stiffness matrix? We have to put all the stiffness coefficients that we have calculated. K11, the first element. K21, the second element of the first row. K12, the first element of the second row. K22, the second element of the second row. This is the rotation. This is the moment caused by the unit rotation. This is the moment caused by unit rotation. We want the full moments. So you multiply it by the displacement, theta 1, theta b, and theta c. That is delta 1, delta 2. The moment caused by these rotations, theta b and theta c, should be equal and opposite to the unbalanced moment. So it is minus the force matrix, that is F1 and F2. This means you substitute all the values calculated, take EI out, and delta 1, delta 2 are the two displacements, theta b and theta c, and these are the force matrix values. And here in this, as per the matrix algebra, you can calculate the values of EI theta b and EI theta c, and that comes to 767.19 and 1783.6. This is just matrix algebra. You can go through the website or some other book for solving these things. Now we have to write down the equation for the member end moments. MAB is equal to M of AB plus 2EI by L into theta B. What about theta A? Theta A is 0. A is fixed, so theta A is 0. And we are MAB we are calculating. MAB is equal to M of AB plus 2EI by L into theta B. Theta B is the farther side. M of AB plus 2EI by L into theta B, that comes to this much. It is minus, so it is anti-clockwise. This is the free body diagram. This minus means anti-clockwise movement. It is done here. Now MBA is equal to M of BA plus 2EI by L into theta B, because it is the near side rotation. Once you apply the value of EI into theta B, you are getting 489.85. It is positive. It is positive means clockwise. It is written here, clockwise. Now M of BA is equal to M of BC. Otherwise, the equilibrium will not be satisfied. M of BA is equal to M of BC. You can also verify by writing the equation M of BC is equal to, MBC is equal to M of BC plus 2 EI by L into theta C plus 2 EI by L into 2 theta B. You can find out the effect of the rotation at B as well as the C. You can write down the equation for MAB in terms of M of AB, theta B and theta C. Here, for the sake of brevity, we have straight away taken M of BC is same as M of BA. You cannot verify that. So M of BC is equal to equal and opposite minus this much. M of CB is equal to 0 because simply supported end, there is no continuity. The equilibrium has to be satisfied. Now we have to draw the free body diagram. First span is 8 meter. Draw the load 200 kilonewton. These are all the member and moments. This is member and moments. Now calculate the two reactions at A and B due to the effect of this load 200 kilonewton as well as the moment 489.85 and also the moment 101.95. By taking moment at A, you will get this reaction, and by taking moment at B, you will get this reaction. These reactions are the effects of this middle load 200 kilonewton as well as the effects of the two moments at A and B. Now, what about the free body diagram for BC? It is loaded with uniformly distributed load 60 kilonewton meter, and there is one end moment 489.85. Now you have to calculate the two reactions at B and C. These reactions are calculated due to this uniformly distributed load as well as due to this moment. If you take moment about B, you will get this reaction. Similarly, if you take moment at C, you will get this reaction at B. Now we have to draw the shear force diagram as well as the bending moment diagram. You can proceed from left. This is the load 51.5 left upward. We will keep it as negative. Then between A and B there is no load. That means it is a straight line. At B there is a load. It is left downward, which is positive 200 minus 51.5. That is 148.5. This is 148.5 positive. Between this point and B, there is no load. So it is a horizontal line. Now at B, you have one load 148.5. It will balance the downward load of 148.5, which is due to 51.5 and 200. Then you have this load of 349. This is left upward. That is again negative. So it is 349. And what about this value at C? It is right upward. It is positive. Left upward is negative, means right upward is positive 241. Between C and B, there is one uniformly distributed load. So you should be connected by a straight line. It should be disconnected by a straight line. If there is no load, it should be connected by a horizontal line. If there is uniformly distributed load, it should be connected by a straight line. So this is the shear force diagram. Now what about the bending moment at midspan of AB? Bending moment at midspan of under the load AB is this much, 51.5 into 4 minus 1095. You can calculate. This is 51.5 into 4 minus 101. So this is 104.05. So this is the bending moment under AB. This is the net bending moment at AB. This is the bending moment at under the load B, the sagging bending moment. And what is the bending moment at the midspan of BC? This is 251 sagging bending moment right upward into 5. That is the first term, 251 into 5 minus 60 into 5 square by 2. So this is 505. This is the net bending moment at midspan of BC. At A, we have got the member and moments 101.5. At the midspan, it is sagging bending moment 104.05. This is the midspan of AB. Between these 2 points, there is no load. So in the bending moment diagram, join it by means of a straight line. At B, the net bending moment is this much, 489.85. We have already calculated MBA and MBC. It is hogging bending moment. Between the midspan point and B, there is no load. Join them by means of a straight line. And in the midspan of BC, this is the bending moment. Between C and this midspan, uniformly distributed load is there. Join it by means of a curve. Then between this midspan and B, you have uniformly distributed load. So join it by means of a curve. So this is the bending moment diagram. As I have already told, there are several explanations needed. What is the relationship between the end member moments and the fixed end moment? What is the relationship between the fixed end moment and the moment caused by the settlement of the support? What is the relationship between the end member moment in terms of fixed end moment and also the rotations? And if what is the moment caused by the rotations? For all these things, we have the relations derived in the slope deflection method, as well as other explanations available in this website, rgnsite.wordpress.com. Please visit this site. This site gives you hundreds of university questions solved on various topics like RCC design, steel design, strength of materials, structural analysis 1 and 2, moment distribution method, slope deflection method, matrix methods, etc. For all these hundreds of solved university questions, please visit rgnsite.wordpress.com. Also, pass on this message to other engineers and students. The download is free. Thank you all.